Today, we will delve into two vastly different yet equally intriguing realms of knowledge, from the profound connections between our inner world and nature to the majestic cosmic phenomena that ripple through the very fabric of space-time. In daily life, many individuals contend with a spectrum of challenges related to their bodies and well-being. These include a persistent struggle with excess weight, distorted self-perception, debilitating episodes of overeating, and at times, uncontrollable compulsive or emotional eating. The relentless cycle of endless diets, chronic digestive issues, unexplained fatigue, and fluctuating moods also fall into this extensive list of trials. These deeply personal issues have long warranted thoughtful discussion. It's important to note that, regrettably, this topic often evokes fear or judgment in society. Therefore, it is crucial to emphasize, the following discussion does not aim to accuse anyone, induce guilt, or suggest that anyone's actions are inherently wrong. Instead, the primary objective is to encourage deep and reflective consideration of a profoundly significant possibility. Perhaps many of the challenges concerning nutrition, body condition, and overall health in the modern world are rooted not solely in food itself, physiology, or medical aspects. There is a possibility that their origins lie much deeper, touching upon the fundamental foundations of existence. This refers to the concept of humanity's relationship with its environment, with nature itself. Such an idea might initially seem somewhat unusual, perhaps even abstract or esoteric. However, it is undoubtedly an aspect that merits the closest attention and profound contemplation. Day by day, more evidence of this interconnectedness emerges from practical work with numerous individuals, making this topic exceptionally relevant to everyone. Transitioning from the world of personal well-being to the boundless expanse of the cosmos, we turn our attention to one of the most astonishing scientific achievements of our time. In September 2015, the world's attention, extending far beyond narrow scientific circles, was captivated by a truly unprecedented discovery. For the first time in human history, astronomers directly witnessed the titanic cosmic dance, the collision of two supermassive black holes. These colossal objects, which had existed for millions of years as gravitationally bound partners, ultimately merged into a single, even more massive and powerful entity. In the process of this monumental merger, they generated unparalleled disturbances in the very fabric of space-time. The echoes of this colossal event, carrying information about the universe, traversed billions of light-years before reaching the most sophisticated and sensitive detectors ever conceived by human ingenuity. This heralded a new era, allowing scientists not just to see the universe through light, but also to hear it by detecting its gravitational pulsations. But what exactly are these mysterious gravitational waves? How might they influence our reality? And why does this cutting-edge, rapidly evolving branch of astronomy attract such immense attention and resource investment? The answers to these questions reveal astonishing new horizons of knowledge. To delve into the phenomenon of gravitational radiation, it's fitting to begin with a look at one such observatory. The image depicts one of the world's two largest and most renowned gravitational wave observatories. This facility is, in itself, a true marvel of engineering and a testament to supreme precision in design. The reasons for its complexity will be revealed later, but for now, let's focus on its unique form and name. This is LIGO, an acronym for Laser Interferometer Gravitational Wave Observatory. Despite the word observatory in its name, one won't find the familiar enormous dome housing an optical telescope here, nor massive parabolic antennas designed to receive radio signals from space. This is because LIGO is not an observatory that operates within the electromagnetic spectrum. In other words, it does not interact with visible light, radio waves, X-rays, or gamma radiation. While some sources of gravitational waves can indeed simultaneously emit electromagnetic waves, their detection is not a prerequisite for LIGO. Gravitational waves are not part of the electromagnetic spectrum. They are an entirely different, fundamentally distinct physical phenomenon. Curiously, even each of us, when moving with acceleration through space, technically emits gravitational waves. The same applies to apples falling from trees, cars moving on highways, or airplanes gaining altitude. However, The masses and accelerations of all these objects are far too small to generate sufficiently perceptible disturbances in spacetime. It's crucial to understand, the greater an object's mass or the stronger its acceleration, the more powerful the gravitational wave it generates. This revolutionary idea was first proposed by the great Albert Einstein in 1916, as one of the logical consequences of his fundamental general theory of relativity, which was published a year earlier. Einstein demonstrated that gravity is not merely a force acting in space, but rather a direct manifestation of the curvature of the very fabric of spacetime. In turn, this curvature arises solely due to the presence of massive bodies. The essence of this profound concept was perhaps most succinctly and powerfully expressed by John Wheeler, a distinguished theoretical physicist, who formulated it as, "Mass tells spacetime how to curve, and spacetime tells mass how to move." A key point is that by integrating the concept of spacetime into the physical world picture, general relativity effectively refuted the ingrained notion of space as a rigid, unchanging structure and time as an absolute, unvarying quantity. The mathematical framework of general relativity, conversely, allows for spacetime to stretch, compress, and curve under the influence of gravity. A natural question arises: if gravity represents curved space, then how does it propagate from one object to another in the universe? Here, special relativity comes to the rescue, establishing the strictest limit on the maximum speed for the transmission of any information, the speed of light. This limitation also applies to changes in mass distribution. Let's imagine a hypothetical situation. If the Sun and all its colossal mass were to vanish in an instant, information about this change could not reach various observers faster than the speed of light. This means Earth would continue its accustomed orbit around the empty space for approximately 8 more minutes before the information about the Sun's vanished gravitational pull reached our planet. Thus, gravity, like any other information in the universe, propagates at the speed of light. It is this undeniable fact that leads us to the inevitable understanding and concept of gravitational radiation, a phenomenon that opens up new ways of understanding the cosmos. When gravitational interaction isn't instantaneous, a natural question arises about its propagation mechanism. Albert Einstein sought to unravel this mystery through his calculations concerning gravitational radiation. His path to understanding wasn't direct, but a series of experiments and adjustments eventually led him to the desired solution, expressed in the so-called quadrupole formula. This mathematical expression clearly demonstrates the process of gravitational wave generation from systems of accelerated masses. This phenomenon is remarkably similar to the generation of electromagnetic waves, which are produced by accelerated charges when their quadrupole moment changes. In other words, any change in the speed or mass of matter causes oscillations in the very structure of spacetime, propagating as waves. These waves, like barely perceptible ripples on a water surface, permeate the entire universe, moving at the speed of light. While acknowledging the aptness of the water wave comparison, it's important to remember that it, like most such visualizations, overlooks one dimension. Space is not a perfectly smooth surface, like a calm lake. It extends in all 3 dimensions around us, and it is in these dimensions that gravitational waves propagate. There's another fundamental difference between a serene body of water and the fabric of spacetime. The latter, though capable of deformation, possesses exceptional rigidity, which prevents it from bending easily, and consequently, the amplitude of its waves remains extremely small. This is why gravitational waves are extraordinarily, even microscopically, tiny. Due to this characteristic, Einstein initially believed their detection would be impossible. However, by focusing efforts on studying astrophysical objects, the most massive bodies in the universe, moving at the highest possible accelerations, and by applying advanced technological achievements, humanity has discovered a real possibility of registering them. Detecting these waves is critically important because they can carry information inaccessible through electromagnetic astronomy methods, including valuable clues to understanding the very nature of gravity. Essentially, a gravitational wave represents a fleeting deformation of the very fabric of spacetime, causing it to alternately stretch and compress at right angles. This means that distances between any objects periodically increase and decrease, determined by the frequency of the passing wave. This inevitably raises a curious question: what are the consequences of such deformation for matter? Are gravitational waves capable of causing distortions in material objects, meaning, can they stretch and compress, for example, the human body? The answer to this question appears to contain both yes and no. A human, like everything else, is composed of atoms, which are essentially vast empty spaces with electrons and protons sparsely distributed within. Consequently, the deformation of space-time would seemingly affect us too. However, it's important to remember that the atoms in our bodies do not exist in isolation. They are strongly bound together by powerful electromagnetic forces. Thus, the degree of potential stretching or compression depends on how much the gravitational interaction surpasses the strength of atomic bonds. Given that gravity is recognized as the weakest of the four fundamental interactions, it appears that it loses in this contest, and therefore, neither planet Earth nor the animals inhabiting it will undergo noticeable deformations. Nevertheless, the reality is even more astonishing. The amplitude of gravitational waves is an infinitesimally small quantity, to put it mildly. The oscillation that a gravitational wave from the most powerful astrophysical sources can cause is approximately 10 to the minus 21st power meters. This value is so insignificant that it can be compared to the size of an elementary particle of an atom, such as a proton. In fact, this magnitude is roughly 10,000 times smaller than the diameter of a proton. In light of such scales, speaking of any significant influence of gravitational waves on matter is practically out of the question. Oscillations that are thousands, and even tens of thousands, of times smaller than the size of a proton simply indicate that gravitational and electromagnetic forces do not contend at the atomic level, as no perceptible oscillations occur there. Technically, objects do stretch and compress along with space itself, but by such a negligible amount that this effect is virtually imperceptible. And it is this microscopic magnitude that astronomers worldwide strive to detect, which makes this task incredibly challenging. However, it is critically important to realize that the amplitude of oscillations is directly proportional to the proximity to the source, so relatively close to the epicenter, gravitational waves can reach millimeter values. Such power is already perceived as a serious destructive force which, depending on the frequency, could cause significant harm to an organism, making it advisable to keep a safe distance from such sources. Before delving into the description of the high-precision instruments humanity has created for such exceedingly delicate measurements, it's necessary to examine the primary sources that generate these waves, as well as their dynamic behavior over time. It is well known that cosmic space abounds with numerous objects of colossal mass capable of significant acceleration. Among these, pairs of black holes or neutron stars undergoing mutual rotation stand out, as do mixed configurations where a black hole and a neutron star form a binary system. Undoubtedly, each of these astronomical phenomena produces its unique set of gravitational wave signals, as binary systems differ in the masses of their constituent elements, the characteristics of their orbits relative to each other, and their distance from Earth. All of them, however, share one common feature that is reflected in gravitational waves. Sooner or later, binary systems of neutron stars or black holes inevitably collide. The question arises, why does this happen? Shouldn't they endlessly orbit within their systems without encountering any obstacles? It turns out that gravitational waves themselves serve as that obstacle, that fundamental reason why these massive objects inevitably draw closer. This is a direct consequence of the fact that gravitational waves are not some abstract concept devoid of influence. On the contrary, they represent an absolutely real physical phenomenon capable of carrying energy. Consequently, if gravitational waves carry energy away, then the objects that generate them inevitably lose this energy. In the case of a binary system of compact objects rotating around each other and emitting gravitational waves, they will lose energy by decreasing their angular momentum. This means their paired orbit will not be eternal. They will gradually approach each other, and they will have no choice but to eventually collide or merge into a single entity. It was this unique ability of gravitational waves to influence binary systems that first allowed for their existence to be confirmed. In 1974, two distinguished astronomers, Russell Hulse and Joseph Taylor, using the Arecibo Radio Observatory, discovered a binary pulsar located 21,000 light-years from Earth. Since pulsars are neutron stars that emit radio signals, general relativity predicted that precisely this type of system should actively emit gravitational waves. Inspired by this, Hulse and Taylor decided to test Albert Einstein's predictions. They began meticulously tracking the radio emissions from this system, aiming to determine if the orbital period of its components changed over time. It took the astrophysicists only 4 years to convincingly confirm. The period was indeed slowly shortening, indicating that the two objects were approaching each other at a speed that precisely matched the predictions of general relativity. For this monumental discovery, Taylor and Hulse were awarded the Nobel Prize in Physics in 1993. Since then, numerous scientific teams, studying pulsar radio emissions, have also identified similar effects, and at that moment, this served as the primary indirect evidence for the validity of gravitational wave theory and general relativity as a whole. However, all these confirmations were in one way or another indirect and only hinted at the reality of gravitational waves. One of the greatest breakthroughs in astrophysics and science in general was their direct detection, when in 2015, the LIGO Observatory for the first time physically recorded the elusive disturbances in spacetime. Gravitational waves, generated by the merger of a pair of black holes, traveled 1.5 billion light-years through the vast expanses of the universe, and were registered by the most sensitive detectors on the planet. This historic moment forever entered the annals of science, and effectively marked the birth of a new era in astronomy. Such incredibly faint oscillations of the universe's fabric are today detected using specialized equipment known as an interferometer. The LIGO detector, which will be examined as an example, consists of two perpendicularly arranged arms, each 4 kilometers long, thus forming a characteristic L shape. From a construction standpoint, it is an extraordinarily complex engineering project, yet its basic operating principle is simple enough to understand. A powerful laser beam is directed onto the surface of a beam splitter. This surface is only partially reflective, so one part of the beam is transmitted and travels along one arm of the interferometer, while the other part is reflected and follows the second arm. Both beams then reflect off mirrors located at the ends of each arm and return to the beam splitter to recombine. It is at the moment of their meeting that a key phenomenon occurs: interference. For those familiar with the principles of interferometer telescopes, this concept is already known. For others, it's important to understand how two light waves interact when superimposed. The principle is quite simple. When the peaks of one wave coincide with the peaks of another, or troughs with troughs, they mutually reinforce each other, and the resulting wave has twice the intensity. In other words, the light becomes brighter. This phenomenon is called constructive interference. If, however, the peaks of one wave overlap with the troughs of another, both waves cancel each other out, meaning they are completely extinguished, and physically no light is observed. This is called destructive interference. Of course, intermediate interaction options are also possible, where the resulting wave can acquire varying intensity depending on the relative phase position of the two original waves. Returning to the LIGO interferometer, it is designed so that once the two separated laser beams reflect off the mirrors and recombine, they should interfere destructively. This means the waves mutually cancel each other out, and the outgoing beam simply disappears, not reaching the detector. But what happens when a gravitational wave passes through this complex system? As mentioned, such waves cause oscillations in the very fabric of spacetime, alternately stretching and compressing it. These oscillations, in turn, affect the interferometer arms, which also slightly stretch and compress. Thus, the laser beams are forced to travel unequal paths before they are meant to recombine. When these beams subsequently converge, they lose synchronization, falling out of phase, and are no longer able to form a distinct destructive interference pattern. Instead, the combined beams create a non-uniform interference pattern, which essentially manifests as a flickering of the laser beam, synchronized with the movement of gravitational waves through space. It is this characteristic flickering that is the target of astronomers' observations, who are, in essence, registering oscillations in the very fabric of spacetime. It should be noted that LIGO's design deliberately incorporates 4-kilometer-long arms, because the greater their length, the easier it is to perform precise measurements. The magnitude of deformation, that is, stretching and compression, directly correlates with the arm's dimensions, and at kilometer scales, the detectable displacement reaches approximately 10 to the minus 18th power meters, which somewhat simplifies the challenging task of detection. Nevertheless, even a length of 4 kilometers remains insufficient for effectively hunting for gravitational waves. The detector's dimensions are also dictated by the wavelength that needs to be captured. It is fundamentally important to distinguish between a wave's amplitude and its wavelength. Amplitude represents the height of the oscillation peaks, that same minuscule quantity whose detection is fraught with immense difficulty, whereas wavelength defines the distance between successive peaks. Gravitational waves, unlike their amplitude, can possess significant length, measured in hundreds of kilometers. For example, for a characteristic gravitational wave with a frequency of 100 Hz, its wavelength reaches 750 kilometers. Consequently, the optimal arm size for a detector designed to register such waves should be at least a quarter of their length, which is nearly 190 kilometers. The secret to LIGO's successful discoveries lies in its constructive complexity, which is significantly more sophisticated than the simplified diagram usually presented. To greatly increase the effective path of the laser beam, an additional mirror was integrated into the standard architecture of each arm, positioned in close proximity to the beam splitter. Thus, after the laser beam enters the interferometer and is subsequently split, each of the resulting beams in each arm reflects multiple times, approximately 300 times, between two mirrors. Only then does it recombine with the beam that traveled along the other arm. As a result, the actual path traveled by the laser beam increased from the initial 4 kilometers to an impressive 1,200 kilometers. Such an engineering solution significantly contributes to enhancing the overall sensitivity of the instrument. Beyond the length of the arms, another critical factor limiting the capabilities of interferometers is the power of the laser radiation used. Essentially, the greater the number of photons converging from each arm, the clearer and more distinct the interference fringes the photodetector can register. However, the initial laser integrated into the interferometer system typically produces only about 40 watts, whereas optimal operation requires power on the order of 750 kilowatts. Building a laser with such initial power is, to say the least, an extraordinarily difficult engineering task. This is why, in this situation, an unconventional solution was employed, with a mirror again playing a crucial role. This device was named the power recycling mirror. The concept involves its placement directly before the laser beam splitter. The initial light beam passes through this mirror from its reverse, transparent side. The beam then continues its path through the interferometer, performing its functions. However, before completing its route and reaching the photodetector, the beam is inevitably directed back to the recycling mirror. This time, it reflects off its surface, returning into the interferometer as if beginning a new cycle. It is crucial to note that at this moment, the laser does not cease its generation, continuously emitting new portions of light. Thus, each reflected beam effectively superimposes on the newly generated light, thereby amplifying it. As a result, the initial few tens of watts of power steadily increase with each reflection of the beam from the recycling mirror, reaching hundreds of kilowatts. Consequently, there is no need to create a super powerful laser. It is sufficient to ensure its self-amplification during the light's passage through the interferometer. However, it becomes evident that even possessing a highly sensitive and powerful interferometer by no means guarantees immediate detection of gravitational waves. Since spacetime deformations, expressed as its stretching and compression, manifest at a subatomic level, it's easy to imagine how numerous undesirable external factors can distort these precise measurements. The slightest vibrations caused by minor noise can completely disrupt the experiment. Sources of such interference can include cars driving on nearby roads or even ocean waves crashing on the coast. Furthermore, the presence of even a single molecule in the path of the laser beam can impede such sensitive measurements. This is precisely why laser beams travel through the highest achievable vacuum, maintained within special tubes laid along each arm of the interferometer. This measure prevents sound waves from propagating and minimizes temperature fluctuations along the photon's path. Furthermore, The mirrors in each arm are securely mounted using an extremely complex seismic isolation system, while thousands of sensors continuously monitor environmental noise, allowing it to be correlated with a potential gravitational wave signal. However, even these measures do not guarantee absolute success. For reliable detection of gravitational waves, a single detector is insufficient. A lone detector can only identify a potential signal, but to confirm it's not random noise in the data stream, at least one more, or preferably several, instruments are required. The LIGO project includes 2 observatories located in geographically opposite corners of the United States, one in Hanford, Washington, and the other in Livingston, Louisiana. The distance between these sites exceeds 3,000 kilometers. This significant separation of detectors means each perceives its own unique local background noise. While any single detector might register, for instance, a hammer dropping, it's highly improbable that an identical event would occur simultaneously at 2 distant locations. Therefore, if both instruments record a similar signal, it significantly increases the likelihood that they have captured actual gravitational waves. Computer systems analyzing data from both detectors deliberately ignore signals that differ significantly, and conversely, pay special attention to similar signals arriving almost synchronously. Time also serves as a crucial marker in this process, as gravitational waves propagate at the speed of light. Astronomers can verify whether an identical signal reached the other detector with the corresponding time delay. The actual difference in this case is approximately 10 milliseconds. Thus, similar signals appearing with a much larger interval are also discarded. Even more comprehensive information can be obtained by using a system of 3 detectors located in different parts of the world. By measuring the time difference between the arrival of a signal at each, it becomes possible to precisely determine the region of cosmic space from which the signal was emitted. For this reason, detectors are indeed spread across the globe, forming a global observational network. In addition to the 2 facilities in the United States, the Virgo detector operates in Italy, located near Pisa. There is also one in Germany, known as GEOS 600, and Kagra in Japan became operational in 2020. Another detector is currently under construction in India and is expected to be launched soon. It is important to emphasize that all these detectors utilize laser interferometer technology. However, laser interferometry represents just one of the existing possibilities for detecting gravitational waves. For example, modern astronomers successfully employ the method of precise measurements of pulsar signals. As gravitational waves pass, the pulsation period of these objects subtly changes, allowing them to be used as natural detectors. There are also plans to launch a space-based laser interferometer with arm lengths stretching millions of kilometers. At this stage, it's crucial to understand that these different methods are suitable for exploring various ranges of the gravitational spectrum, or more precisely, different types of gravitational waves. Gravitational waves carry diverse information at different frequencies. In this aspect, they demonstrate similarity to electromagnetic waves. For instance, ground-based interferometers like LIGO operate in the range from 10 Hz to several kHz, while space-based systems will investigate waves in the megahertz range. This means LIGO can register certain events, but others remain beyond its reach. What makes gravitational wave sources so appealing? The fact that some of them eventually manifest at various frequencies, and thus become accessible for observation. Primarily, this refers to binary systems composed of compact objects, namely black holes and neutron stars. These objects are small enough to get extremely close while orbiting each other, allowing them to achieve colossal speeds. At the same time, they possess immense mass, and therefore, generally generate the most significant space-time disturbances. As they draw closer, they accelerate even more, leading to the generation of more powerful gravitational waves. These waves carry away even more angular momentum, and the objects continue to approach each other, emitting increasingly intense waves. Ultimately, they inevitably collide. This phase of gravitational radiation is called the inspiral. It's important to note that as the rotation frequency changes, so does the frequency of the emitted gravitational waves, and at a certain point, they eventually reach the sensitivity range of LIGO detectors. It is at this time that astronomers gain the opportunity to detect a massive collision. It turns out that the systems become visible to the detectors literally seconds before their merger, so the observatory captures only the final moments of this captivating astronomical event. The more massive the objects, the shorter the signal lasts. For example, black holes undergo an in-spiral phase that, within LIGO's sensitivity range, progresses significantly faster than that of a pair of neutron stars. The first historical signal registered by LIGO lasted only 2 seconds. Meanwhile, the first signal from 2 neutron stars, detected in 2017, lasted a full 100 seconds. By converting it into an audible signal, one can literally hear the final moments of the neutron stars' lives. This signal, by the way, made history not only as the first detection of gravitational waves from neutron stars. Event GW170817 was exceptionally well identified by 3 detectors simultaneously, 2 LIGO and 1 Virgo. This allowed for the combination of data and highly accurate localization of the sky region from which the signal originated. Acting quickly, scientists relayed the information to their colleagues at electromagnetic observatories, and just a few hours after the event, an optical telescope in Chile, peering intently at the specified region, became the first telescope in history to observe the aftermath of a neutron star collision. Subsequently, all the world's most powerful optical, X-ray, radio, infrared, and gamma-ray telescopes, as well as neutrino detectors, observed the afterglow of this remarkable cosmic collision. This became one of the most thoroughly studied transient astronomical phenomena in the history of science. In general, since gravitational waves and electromagnetic radiation are presumed to originate from the same source, it might be assumed that they travel together through the universe. However, the situation can be significantly more complex. Gravitational waves are not necessarily synchronous with their electromagnetic counterparts. The reason for this is that light, radio waves, and similar radiation are significantly affected by ordinary matter. Radiation can be absorbed by matter, scattered, or experience additional lensing. However, gravitational waves are free from such difficulties. They interact minimally with matter, continuing their journey through space unimpeded. This property, their weak interaction with matter, is one of their key advantages, as in certain cases, gravitational radiation delivers information inaccessible to electromagnetic waves. For example, gravitational waves reach us directly from the epicenters of the most powerful cosmic cataclysms, supernova explosions during stellar core collapse. Electromagnetic radiation, in contrast, is scattered multiple times by the dense matter surrounding the explosion. It takes days for it to finally break free, but in doing so, it loses most of the details that could tell us about the deep processes accompanying the outburst. In contrast, gravitational waves emerge from there virtually undistorted, if one can put it that way. This makes them an ideal source of information about the most complex aspects of giant